Hello everyone and welcome to today's webinar, What Prevents You from Increasing Your PCR Productivity? I am Jennifer Woods of LabRoots and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Eppendorf. To learn more, visit eppendorf.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the Continuing Education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Aurora Peng, PhD, Field Application Specialist at Eppendorf. Aurora, you may now begin your presentation.
All right, thank you, Jennifer, for the introduction and for your help in moderating. And hello, everyone. It's my pleasure to meet everyone in today's session. First, I'll have to apologize. When I come to the office this morning, I found that the webcam has disappeared, and I couldn't find one that is free for use. So I can't say hello to everyone, which is totally fine, so that I won't be nervous. All right, so jokes aside, in the next hour or so, I'll talk about a nostalgic topic, polymerase chain reaction, or PCR. It's a boring technique, I know. It has been widely used for many decades now, and if you are even slightly involved in molecular biology, you would have experience in doing PCR. And for better experts, this topic is boring to the point of vomiting. I spent almost 2 years of my PhD playing with various PCR strategies to clone several novel sequences, so I can empathize with this feeling. Well, so to prevent myself from getting cursed at for presenting such a boring topic, I've chosen to focus on some less known facts or hidden technologies associated with PCR. Since the theme of today's discussion is on productivity, I'll talk about related PCR hardware, software, and peripheral technologies that can help researchers shorten their time to results. Now, from the perspective of a scientist, productivity is not the first condition we think about when performing PCR. Rather than productivity, we are first concerned about accuracy and sensitivity of the device and reagents we use, which directly affects final reproducibility of our results. For lab managers, installation, upgrade, compatibility, technology lifetime, pricing, maintenance, etc., all needs to be considered as part of total cost of ownership calculation. And of the 3 technical performance criteria I mentioned previously, the most important is reproducibility, because flaws like temperature inaccuracy or low sensitivity can still be solved through technical modifications. But if a PCR system is not reproducible, no amount of effort is going to let you perform your work with confidence. And the key to reproducibility is actually technology. Without technology that can reliably give consistent results, any strategy to increase productivity is fraught with risk. This is why a thermocycler is not just a thermocycler, and not all thermocyclers are made equal. You may argue that all cyclers can replicate DNA, but the question is, how much effort does it take you to produce a working and reliable protocol for each system? Time is a golden resource, not to mention material wastage, including precious samples. So let's talk about the first technology that differentiates different cyclers, which is the thermoblock. A thermoblock in a thermocycler consists of 3 main parts: the topmost vessel block to accommodate plastic vessels, and the bottommost heat sink to dissipate heat. What we want to focus on now is the layer between the two. Directly below the vessel block are peltiers, which are controlled by electronic circuits to provide varying degree of heat. These 3 parts, the vessel block, peltiers, and heat sink, are fixed together into a whole unit. The key point here is each Peltier is actually a sandwich board consisting of multiple heating elements. Notice that where you have the fixing point, you can't actually have any heating elements there. Thus, how many Peltier boards are used, how many circuits control these Peltiers, and where an engineer places the fixing points will have an impact on the heat distribution of the thermal block. This frequently affects the temperature accuracy, precision, and homogeneity across the block. Take this design here as an example. There are 6 Peltier boards, each covering 4x4 well area beneath the vessel block. The fixing point is in the middle of each board and does not overlap with any of the standard 96 well positions above. This means that all well positions have a full panel of heating elements directly underneath. The reason I draw attention to this point is because this is not the only design used in thermal cyclers. Some cyclers may use side fixing strategy, which means that the Peltiers are fixed to the block at 2 sides of the Peltier. Remember that you cannot have any heating and cooling elements at the fixing points. Thus, side fixing basically means that there will be some well areas that do not have heating elements directly underneath. These wells rely on heat generated by adjacent heating elements, and from the perspective of heating homogeneity, there would be a difference between these wells and the wells that are fully supported by direct heating underneath. In other words, such cycler would effectively have Peltier areas smaller than the thermal block. In contrast, Peltiers with fixing positions outside of the actual wells, such as used in the center fixing design, allows the entire block to have the same heat profile. The center fixing strategy also has another advantage. The single fixing point in the middle distributes the mechanical stress from fixing evenly in a radial manner. Additionally, it allows bigger leeway for compensating the mechanical stress from expansion and contraction of heating elements in the Peltier board during heating and cooling. And this reduction in mechanical stress consequently results in a longer lifetime of the thermal block. The effect of temperature homogeneity from different thermal block design is apparent when comparing results of temperature-sensitive PCR system. Running replicates from the same master mix at different well positions, that is, the corners, the sides, the centers, would make obvious the design of a thermal cycler and the actual usable well areas of a thermal block. You can see from the gel photos here comparing the results from 2 cyclers. Both target amplicons were consistently amplified with the master cycler X50. In the other thermal cycler, you can see that the reproducible amplification is limited to the center of the block, and the worst performing well locations are at the corners. From these results, we can infer that the side fixing strategy of Peltiers are probably used in this cycler, consequently leading to effective heating areas smaller than the vessel block. In such cases, one can only safely use the well areas at the center, which means there is a 37.5% loss of throughput in every PCR run. Hence, if you are concerned about ensuring maximum productivity, choosing a thermal cycler with the right Peltier fixing technology is important, or you might find that you would inexplicably lose time, money, and biological resources down the line. Now, taking a peek into a manufacturer's technology is often not easy to do. At the end of the day, it really depends on the manufacturer's confidence in their technology to reveal these little secrets to you. So now let us take a look at what we researchers have more control in. That is, what can we do to shorten PCR runtime and thus increase overall productivity? PCR is often seen by researchers as a workflow bottleneck due to the amount of time a run can take, and the PCR step itself is often neglected in most workflow efficiency transformation efforts. In fact, each part of the PCR workflow can be optimized. You can optimize the program, change to a faster cycler, or use PCR vessels and reagents meant for fast PCR applications. The first strategy is to rely on technical scientific knowledge. There are various ways to cut down on PCR runtime by modifying run parameters or program settings as long as you understand the nature of your template and the reagent that you use. For example, reducing the denaturation temperature to the limit that wouldn't affect amplification means that the cycler needs less time to climb the extra few degrees Celsius. Depending on the length of your template and its GC content, you can reduce or even eliminate the initial denaturation step. Similarly, the rule of thumb for extension time depends on the processivity of the enzyme that you use, which is commonly about 1,000 base pair per minute, and the optimal activity at 72 degrees Celsius. This means that if you need to replicate a 1 kilobase amplicon using enzyme with this processivity, then the extension time is 1 minute, and you can actually reduce this time accordingly when amplifying shorter amplicons. Some literature has found that increasing the extension temperature can also increase amplification efficiency. With this in mind, the final extension step is usually a safeguard step in case full extension of amplicons was not completed under the set holding time. Thus, if the enzyme you use has good processivity and is fresh, that is, the enzyme activity hasn't been compromised by frequent exposure to higher temperature during use, then the final step can actually be eliminated. Next, if your starting template concentration is high, or if this PCR system is sensitive and efficient, then you can reduce the number of cycles, especially if amplicon U is not your goal. And finally, a few seconds from each of the looping steps can be shaved off through optimization. Now, this might not look like a lot, but if you can reduce even 15 seconds out of 3 steps, then that's 15 seconds times 30 cycles, which is 7.5 minutes time saving. Another strategy that requires less technical content and effort is by switching to a 2-step protocol by combining the annealing and extension steps. This is possible because while specific annealing occurs at temperatures specific to primers, DNA polymerase has activity at almost any temperature above room temperature. The enzyme works at its optimal efficiency at 72 degrees Celsius, which is why the extension temperature is normally set at this temperature, but it will also work, albeit at a slower rate, at lower temperatures. In the combined step, the holding time only needed to be slightly longer than the time used in 3-step PCR, thus saving time from shorter holding duration, as well as cycling RAM time between temperatures of the 2 steps. Take the example shown in this slide. By combining the 2 steps into one alone, shorten 12.6% runtime, which can be further optimized and reduced. Naturally, 3 to 2-step PCR strategy is not always suitable. It is not suitable for long template amplification due to the slower activity of polymerase at lower temperature. And this is also the reason why almost all real-time PCR use 2-step protocol, because most of the amplicon length of qPCR is generally in the range of 150 to 200 base pair. So it is less affected by the decrease in amplification efficiency. And for the same reason, it is also not suitable for systems with primers requiring lower annealing temperature. Additionally, if the primers are likely to form dimers, it is better to use 3-step PCR. This would decrease the incubation time at the annealing step and limit primer-dimer formation. But these problems aside, 3 to 2-step strategy is a good way to shorten total PCR runtime and increase productivity. Now, the second strategy is to use thermal blocks or thermocyclers with higher speed. For example, the choice of thermal block material is between higher ramp rates or better temperature homogeneity. We know that silver blocks are faster than aluminum blocks, but aluminum block is better at temperature control and hence has relatively better overall temperature performance. Now, when comparing the speed of thermocyclers from different manufacturers, the first specification to look at is usually the heating and cooling ramp rates. Actually, there are two aspects related to ramping rates. On top of being faster, a higher number generally means that the working ramping range is wider. Hence, when one needs to adjust the actual ramp rate according to the needs of the protocol or application, the flexibility is higher. However, if the key point is on the word fast, that is, the goal is to complete a run faster or consequently increasing productivity by running more PCRs in a day, then comparing ramp rate specifications of different cyclers on paper would not reflect the true speed of thermal cycler. With the same protocol, it can take 44 minutes on one cycler, while another cycler next to it may take twice as long. And the reason for this is not entirely due to the differences in maximum ramp rates between different cyclers. This can be seen by a comparison study done on 12 different thermocycler models commonly seen in the market. Ignoring those with different published ramp rates, 5 thermocyclers highlighted here has technical specification of 5 degrees Celsius per second, and they were found to complete the same PCR protocol at different times. And what is more noteworthy is that the time differences can be as much as 11 minutes apart. On the other hand, it is also possible that two cyclers with published ramp rates that look far apart can finish the same protocol at the same time, with the cycler having lower technical data on paper, finishing even a few seconds faster. So the question is, why does this happen? Now, the main reason is because there is no unified standard that a manufacturer has to follow when it comes to measuring and publishing ramp rates. Hence, in the technical data sheets of different cyclers, you would commonly come across terms like maximum ramp rate, average ramp rate, measured ramp rate, etc. But what exactly do these mean, and how does it influence speed? The graph that you see here is a common temperature curve graph of a thermocycler. You would think from this graph that the ramp rate of a cycler can be easily calculated from the gradient of the curve. But in reality, the heating and cooling rates may not be uniform along the whole temperature line. Often, what maximum ramp rate meant on technical data sheet refers to the maximum achievable heating rate, which applies within a small temperature range, for example, 75 to 79 degrees Celsius illustrated in this graph here. This means that if the maximum ramp rate on paper is 8 degrees Celsius per second, the cycler only runs at this speed for 0.5 seconds every time the temperature cycle crosses this range. For the rest of the time, the thermocycler runs at a much slower speed, that is, the average ramp rate. Hence, it is important to understand the ramping behavior of your cycler, and especially so in choosing a high-speed cycler. Only thermocyclers with linear ramping technology have corresponding speed that accurately reflect its technical data. And cyclers with variable ramp rate would perform slower than implied by this published technical data. Moreover, the importance of linear ramping is not limited to speed, but also for result reproducibility. Variable ramping can affect PCR results of PCR systems that are sensitive to reaction speed, such as certain forensic and NGS kits. Variable ramping behavior also makes it difficult to transfer PCR program to another thermocycler model, since you can't say what exactly is the exact ramp rate to follow or to program. Now next is to discuss the influence of PCR vessels on productivity. If cycler speed is improved by increasing temperature performance, then the improvement on PCR vessels concentrates on speeding up heat transfer, that is, from the block to the reaction. The common strategies to achieve this are to make the walls of the vessels thinner, or to increase the volume to surface area ratio that is in contact with thermal block. The former is limited by the fragility of the polymer material, which is typically polypropylene, because polypropylene is a highly malleable and hence suitable for making thin wall vessels, but precisely because it is soft, it is fragile and difficult to handle, so there is a limit to how thin one can go making it. The latter strategy involves making smaller vessels or even changing the shape of the vessels to increase the surface area ratio. However, the disadvantages are obvious. Special consumable formats require special devices. This kind of closed system might be okay for diagnostic applications that has high system repeatability, but are unsuitable for research and development work and subsequent throughput expansion via automation. Recently, another innovative strategy was developed, that is to attack the root of the problem itself, which is heat transfer. Special format is not desirable, then we keep the existing shape. And if polypropylene is fragile and cannot get thinner, then we keep the same thickness and use another material that has higher thermal conductivity. And the polymer that fits this characteristic is polyethylene. It is as malleable as polypropylene, but has a much higher thermal conductivity than polypropylene. Hence, it is able to transfer heat faster from the thermal block to the PCR reaction mix. Studies conducted to compare the amplification results of this polyethylene tube with different polypropylene vessels under the same condition showed vastly improved amplicon U. This means that using this kind of vessels, you can potentially cut down on PCR holding times or number of PCR cycles, hence achieving shorter time to result. Moreover, this polyethylene fast PCR vessel is suitable to be used to troubleshoot low-yield amplification. There is no need for additional investment into special devices or systems, so the cost of stepping up productivity is much smaller. Last is a strategy targeting PCR reaction mix. Although all uses DNA polymerase for amplification, there are slight differences in polymerase development and reaction mix formulation in the market. I won't expand on the simplest methods of reducing reaction volume and adding components such as DMSO to the reaction mix, because it is self-explanatory and has a lot of literature on such topics. But have you ever noticed or wondered why certain kits recommend denaturation temperature at 95 degrees Celsius or 98 degrees Celsius, and how does this impact your experiment? According to a report in Neuroscience, 2 different kits were used in an attempt to amplify long sequences from the tilapia fish. ABI amplitide gold was used initially to amplify short fragments within the genes. However, amplification success was greatly reduced when amplifying longer fragments, especially after the length passed 2 kilobase pair, and it actually totally failed to amplify a full-length sequence of 2.7 kilobase long gene. To solve this, Takara XTAC-HS was used. Both the amplitide gold and the XTACs are actually hot start enzymes designed to reduce non-specific amplification. However, amplitide gold is a chemically modified hot start enzyme which needs to be reactivated by heating at 95 degrees Celsius for about 5 to 15 minutes. Now, this condition is harsh and could cause depurination and scission of DNA, so it is found to be incompatible for use in effective and accurate amplification of long fragments. For this reason, the exact enzyme which is antibody inactivated was found to be more suitable. Now, the bring-home message is that there is a reason why so many enzymes exist in the market and why many manufacturers invest in producing new and improved PCR reagents, despite this field being a mature market. As can be seen from this study, without considering anything else, just a switch in enzyme alone shortened the total PCR runtime by 18.5 minutes. That's a lot of time. How much can you do in 18.5 minutes? Well, the answer is if you complete an entire PCR run, you can do that if you're using the right system. For example, a specially formulated reaction mix that are meant for fast PCR, such as the new Promega GoTech Rapid Master Mix used in this comparison here. This slide here summarizes all the learnings from the previous 4 parameters. If it usually takes about 90 minutes to finish a 3-step PCR, amplifying 1 kilobase per target DNA using conventional reagent, you can change to a fast reagent like the Promega GoTech Rapid Master Mix here, and then use it in combination with polyethylene fast consumables. Then run it on a high ramp rate cycler like the Master Cycler X50, and you can cut down the time to a terrifying 16 minutes to complete a run from the previous 90 minutes. This means that if you used to run 5 PCRs a day, you can step up the productivity to 30 runs, thus gaining a full 500% of productivity. And if you further optimize the program to a 2-step protocol, you can save another 4 minutes. Now, this might not sound like a lot, but because the time for a full run is only 16 minutes, you can run 10 more PCRs in a day. So a workload of 150 runs that takes a week can now be completed in less than 4 days. Now, we've visited both cycler and peripheral technologies, as well as techniques that directly impact speed in improving PCR productivity. Next, I would like to talk about other technologies that indirectly improve workflow efficiency by making PCR less complicated and more organized. A few years after thermocyclers were commercialized, the technology called gradient was introduced, which can be considered as a revolution in doing PCR-based research. What is called gradient technology is to generate a temperature gradient across the thermal block. This is especially targeted to the problem that optimal temperature of primer annealing requires practical trial and error. Being able to run multiple temperatures in a single step enable researchers to test a range of temperatures for optimal primer annealing in the same run. Now, there are several reasons why few people use the gradient technology to optimize parameters other than the annealing temperature, for example, the denaturation temperature. Because usually, unless the DNA template has special characteristics such as high GC content or secondary structures, the default temperature designed by the enzyme manufacturer can do the job well. But mainly, it is because there's too much trouble to optimize the denaturation temperature on top of the annealing temperature using conventional gradient technology. Because after you have optimized one parameter, then work on the other, you might find that the previously so-called optimized temperature can no longer work or become unsatisfactory. So, to solve this, a new revolution in the area of gradient technology was introduced a few years ago. This improved gradient technology is called 2D or two-dimensional gradients, which allows the temperature gradient to be applied in 2 different directions simultaneously. This effectively enabled 2 temperature variables to be tested at the same time in a single PCR. And the benefit of running two-dimensional gradient is that it provides a complete behavioral profile of both DNA template and primer's characteristic. By running the complete temperature span for both denaturation and annealing temperatures, it is possible to choose the optimal conditions to meet desired experimental objective. For example, in this combined optimization of two-dimensional parameters across 96 wells, we can determine that 97 degrees Celsius denaturation plus 70 degrees Celsius annealing achieve best specificity, while 93 degrees Celsius plus 66 degrees Celsius gives the best yield. And for best balance, 97 degrees Celsius plus 68 degrees Celsius combination is the best option. Now, naturally, the 2D gradient can be used in other than new PCR projects. The most attractive aspect of this improvement in gradient technology is that it is useful in improving existing optimized systems. Take this example reported by a research group in the Max Planck Institute. And if you can see here, at denaturation temperature of 98 degrees Celsius and the gradient profile of annealing temperature ranging from 50 to 70 degrees Celsius, the target amplicon has a size of about 200 base pair. And according to the gel result here, annealing temperatures within 50 to 65 degrees Celsius range can be chosen as the optimal temperature. Unfortunately, within this range, the problem of non-specific amplification cannot be avoided, as can be seen by the presence of multiple large-sized bands in the gel. And usually when such results were obtained, the most commonly used downstream strategy is to extract and purify the desired amplicons from the gel. If large amount of amplicons is required for cloning, duplicates are run. This way is less tedious than trying to further optimize by fine-tuning other parameters. However, using 2D gradient technology, the process of optimization is similar to using conventional gradient with the same amount of effort. Furthermore, to reduce sample, work, and analysis load, instead of the full 96 well as in the example previously, this group smartly utilized a tempering scheme with 31 samples covering denaturation gradient range of 90 to 98 degrees Celsius and annealing gradient range of 50 to 70 degrees Celsius. And running this analysis on a cycler with conventional 1D gradient would require 8 separate PCR runs, that is, one set of annealing gradient for each denaturation temperature. However, with these 2D gradients, you will get this kind of gel results where, since the goal of this system is to improve specificity, now we can then concentrate on the results in the orange boxes. So you can see that from going down from 98 degrees denaturation temperature, these large-size amplicons, which are non-specific amplicons, first see an increase in yield, which peak at about 92 degrees Celsius, but then they disappeared when the temperature decreased further. And at 90.5 degrees Celsius, no non-specific products were amplified, while the yield for the target amplicon was retained at 56 degrees Celsius annealing temperature. So these results here clearly showed that in just one PCR run, a vastly improved system was achieved using 2D gradient optimization strategy. A single clean band means homogeneous PCR products in a reaction. And this can save much effort in subsequent downstream processing and is highly beneficial for mass pooling purposes. On a separate PCR system, the same research group used 2D gradient to improve amplification result of mouse located gene B with target amplicon size of about 600 base pair. Originally, the gradient optimization result obtained using single denaturation temperature was already optimistic, as shown in this gel photo here at 98 degrees Celsius. However, Further testing using 2D gradient showed that this was actually not the most optimal parameter. The amplification yield can actually be increased by lowering the denaturation temperature. For example, at 90 degrees Celsius, the bandwidth of the target amplicon is almost twice that of the 95 degrees Celsius at the same annealing temperature. Although the benefits in doing so is not obvious in this system, imagine if you are dealing with very low starting DNA concentration or DNA templates that are very difficult to amplify. Such difficulties are generally labor or resource intensive to resolve, but it can be simply resolved using this 2D gradient technology. In conclusion, the new 2D gradient technology can improve specificity, which can give publications a more professional look. It can facilitate post-PCR work and provide better alternatives than tedious strategies like touchdown PCR. And by improving yield, number of cycles and holding times may be reduced to cut down total runtime. Improved PCR efficiency can also reduce various resources, including reaction and sample. And lastly, higher amplification yield is beneficial for downstream processing, as well as facilitate troubleshooting of difficult applications. Now, another aspect worth considering in stepping up productivity is digital transformation. Digitalization is an inevitable trend, and many new systems in the lab are now equipped with various digitally supported functions such as fleet control, remote monitoring, central data management, service maintenance, etc. Now, connected systems allow you to run multiple devices with less manual actions. Usually, there are functions like device booking, maintenance scheduling, and central data storage. All this facilitates lab organization, which would ultimately save time and resources by minimizing risk of errors and resource conflicts. Systems that has throughput expansion capability via connectivity is also a good way to save investment cost. The dependent model is usually priced lower than the master controller, and PC supported via fleet control software is even less expensive, and a single software can control many cyclers, resulting in less average price per device. The last thing you can do to improve lab productivity is the often neglected consideration of service maintenance. Because device maintenance is usually carried out only like once or twice a year, and not all devices at the same time, it is easy to forget that each time this is done, a cycler is out of play for some time. And so the question is, how long is this time for you? There are three types of scenarios. The first is that you call and schedule for a certified service technician to come and perform service and verification of your thermocycler. The time frame for this is difficult to calculate since it depends on how fast you can get the technician to come and what verification system he uses. The second scenario is that you need to send out your thermocycler back to its original manufacturer. Now let's do a calculation and let us be optimistic with our estimates. It takes 1 day to disinfect, pack, and send out the device. Shipping takes 3 days. That's including custom clearance or probably longer for certain countries. It stays at the manufacturer's side if you're lucky enough to meet with a manufacturer's super efficiency for 1 day. And it takes the same amount of time for the cycler to come back to you. Now that means we're talking about at least 8 days of downtime, not counting the weekend. So your cycler might just come back in time after you've taken a long, nice vacation. So the impact of this downtime here, is it big for you? It may not be big for a lab that is not very busy usually, but for labs that pursue productivity, the consequence of work interruption enlarge exponentially with each device. Not only would work throughput be reduced when a cycler is out of service, it also requires rearrangement of work tasks of the involved lab groups during this period. And what's words is that the time frame is totally out of your control. The third scenario is the best option for labs that want to minimize the effect of service interruption and downtime. That is to perform in-house service and temperature verification. You can save on the shipping procedure and time, and if you choose the right system, verification can be completed in minimal time. So it's time to evaluate your current service practice, your service needs, and then choose the right strategy to deal with those devices you have in your lab. Okay, so with that, we've now reached the end of today's webinar. And I've talked a lot about different technologies and knowledge points up to here. So just allow me to make a small advertisement, a very, very small advertisement. All the comparison data that I presented so far use the Appendorf flagship model Master Cycler X50 as the benchmark. These results are only possible due to the specs of this cycler, such as the high ramp rate, 10 degrees Celsius per second heating, being the fastest in the conventional cycler category in the market. Center fixing pellet design and linear ramping technology allows fast completion, reproducible result, and robust use. Its automatic adjustable heated flex lid can accommodate all dimensions of reaction vessels, allowing the use of fast polyethylene PCR consumables, thus forming a complete support system for running fast PCR without additional separate investment. This cycler is also the only cycler in the market with the 2D gradient technology, which allows various optimization strategies to ease experimental challenges and improve results quality and efficiency. And to support high throughput needs, expansion is flexible and economical through networking, while regulatory needs are supported through security functions and comprehensive documentation. So, thank you for your attention. Thank you for listening, and I'm happy to entertain questions from the floor now.
Thank you, Aurora, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you would like to ask, please do so now. Just click on the Ask a Question box located at the far left of your screen. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, since it is not reliable to compare ramp rates to determine cycler speed, how do we choose if we want to have a fast cycler?
All right, so in summary, it is okay to rely on tech data sheets if you want to know the adjustable ramping rate. But if you really want to have a real fast cycler to increase productivity, then it's better to make a total runtime assessment. So you can request that the manufacturer make a comparison of two different cyclers or give the total runtime of the cycler that you're interested in with a specific protocol. And then using the same protocol, compare it with a different brand of thermocycler, and then you can see differences in total runtime. So when comparing this type of data, you can more or less guess what kind of ramping technology they use, whether the maximum ramp rate is really the real ramp rate, or is it just a small part of the ramping, and then most of the time it is at a much slower rate. So in other words, if you really want speed, it's not just about the maximum heating or cooling rate on paper, but you really actually have to compare the real performance.
Thank you, Aurora. Our next question is, will Eppendorf consider qPCR instruments again?
Well, at the moment, there is no real plans. Perhaps when we make an assessment of the market needs, it might be possible.
Okay, thank you. Let's see, our next question here. How can I increase the yield when I have a very thin and borrowed amplicon and doesn't work with reamplification with the same set of primers, and I don't have a primer for a nested PCR?
Well, there are a few strategies to do that. Of course, as I mentioned, if you have a cycler with 2D gradient technology, you can try that by testing a combination of different steps like denaturation and annealing. It is also possible if you increase or decrease certain parameters, because when we're talking about thin amplicon, that means a very low yield. It could be that the DNA template is not opened enough, meaning you don't have enough temperature to open up the DNA, or that maybe it is too stringent for amplification to occur. So you can reduce the denaturation temperature. Sometimes that might help. So there is no fixed answer to that. You have to do a few trial and errors, and this is exactly why the 2D gradient is so useful, because you can test several parameters at one go instead of running like 10, 15, 20 PCRs to test different parameters.
Thank you again, Aurora. Our next question is, you talked mainly about heating. How important is cooling in regards to time saving?
Well, generally the heating is done using the heating elements of the peltiers, and so is cooling. And cooling is helped by the heat sink and also the fan. But due to the oscillating temperature of heating and cooling, the heat sink also accumulates heat while decreasing the temperature. This is the reason why the heating rate is always higher than the cooling rate. So when you have cycler with linear ramping technology, then it is set at a certain rate, and the dependency is not so high compared to cyclers where you have all these average ramp rates. It is controlled much better in doing so. Does that answer your question?
Thank you again, Aurora. If you need further clarification on that question, please just type it into the question and answer box. The next question we have, what do we do if we have multiple bands? Do we just increase the temperature?
Yes and no, because it depends on why you have multiple bands. So increasing the temperature, the theory behind that is to increase the stringency of your PCR, which generally would help, but not always, I would say. So it really depends. Of course, the first thing we do is to increase the temperature, but if you have gradient, of course, again, it is easier to test different parameters and different combinations of parameters. But if you do not have a gradient technology, even a conventional gradient technology, then yes, you can try first go increase the temperature, or you can also decrease the holding time sometimes.
Thank you, Aurora. The next question here, could you please explain again about using two temperatures in the same run?
Right, so the two gradient means that you can make a gradient of the 96 well block in two different directions. So for example, in the denaturation step, you make it in a vertical direction, so from top to bottom. Then when it reaches the annealing step, you change the direction of the gradient to go from left to right. So that means you have a matrix of different combinations. So for example, you have 98 on top, and then 97, 96, 95, going from top to bottom. But at the same time, when you are going to the annealing, you get 98 plus 50 degrees, 98 plus 52 degrees, 98 plus 54 degrees, and so on and so forth. And you get a matrix of 96 wells. So you get a combination of two parameters at the same time in one PCR run. That is how the 2D gradient work and how you can test different temperature in two steps in the same PCR run.
Thank you, Aurora. Our next question, excuse me. What is the best way to achieve sequence amplification for 1.5 kilobase and approximately 500 base pair sequences in a short time?
What is the best way to... Sorry, can you repeat the question, please?
I reworded it a little bit. He says, for 1.5 kilobases and up to or around 500 base pair sequence amplification, what's the best way to achieve that in a short time?
You can try to shave off most of the holding times, actually, if you're using three-step PCR. It is quite robust, so most of the steps in each denaturation, annealing, extension can be shaved off, so you save a few seconds in each step. If your template is high enough in concentration, you can also reduce the cycle number. So 1.5 kilobase pair is not large. Most of the enzymes in the market are very robust for this range of sequence length. So it's quite easy to shave off time. But of course, if you're using fast consumables and fast reagent, you can even shave it to 2 seconds, 3 seconds, 4 seconds of holding time in each step. Just like the example that I showed previously with the fast master mix, you can complete the whole PCR of 1.5 kb in 15, 16, 17 minutes.
Thank you again, Aurora. The next question here. Does heating and cooling affect PCR inhibitors, if any, as much as it affects the PCR products?
Not to my knowledge. So usually if you have PCR inhibitors, depending on the seriousness of the inhibitor presence, whether you use the optimal heating and cooling or not, you will get inhibition, because it's not so dependent on the template itself, but rather it is a kind of contaminant, I would say.
Thank you, Aurora. Our next question. What's the main reason to pick only Eppendorf instruments? What are your major specifications of your PCR when compared to other companies' PCR instruments?
Well, I've talked a lot about the different technologies in this presentation, such as the ramping technology, the 2D gradient, also the heating, cooling rates. All these are unique to Eppendorf cyclers. So if you want a fast cycler, definitely we're the fastest with the X50 family. If you want a reproducible cycler, we have the ramping technology and also the Peltier design, which is really, really useful for reproducible results. And that's also, again, very specific to Eppendorf cycler. So it really depends on what you're looking for. If you're looking for robustness, quality, speed, reproducibility, then we're really top of the line.
Thank you, Aurora. Let's see, we have a few more questions here. Can the rapid enzyme achieve the same results in all conventional cyclers?
Yes, with differences in efficiency. So for example, if the protocol works on one cycler and it doesn't work on another, usually increasing the incubation time of the steps can solve the problems. So additionally, the previous discussed differences in total run times between different cyclers running the same protocol applies, but in general, yes, it can be amplified faster compared to conventional enzymes in all of the cyclers. But of course, how much faster is really also dependent on the cycler itself, not just reagent.
Thank you, Aurora. Looks like that's all we have time for today. Before we go, do you have any final comments for our audience?
Well, not really. So I just want to say thank you for taking the time, and it's a great pleasure to have everyone gather here today. And I hope that my talk is of little help to everyone in the lab. So if you have further questions, of course, do feel free to get in contact with us because a lot of all this science needs more explanation than just a few sentences here live. So contact us at any time, and we look forward to exchange knowledge with you.
Thank you again, Dr. Aurora Pung, for your time today and for your important research. We would also like to thank LabRoots and our sponsor, Eppendorf, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period, will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.